The following case study is an example of how engineered residual compression successfully mitigates gear walk, corrosion fatigue, and stress corrosion cracking in landing gear. Landing gear is manufactured from high-strength 300M steel due to its exceptional durability and fracture resistance. Despite this material's inherent strength, landing gear is still life-limited from stress corrosion cracking, SCC for short, corrosion fatigue, and fracture from vibratory stresses. Repetitive impacts and braking during landing create vibratory stresses known as gear walk, which can lead to fatigue failures. If gear walk occurs when corrosion or stress corrosion cracking is already present, those cracks can rapidly propagate between inspections. The MD-88 fleet experienced 6 such fatigue failures in the main landing gear's shock strut cylinders, resulting in runway collapses. In response, the FAA issued an airworthiness directive requiring hydraulic brake line restrictors to dampen the vibrations. However, existing small cracks continued to propagate, leading to further failures. A subsequent directive mandated repetitive inspections, costing one airline 5,500 man-hours and over $1 million annually, not including losses from downtime. Replacing each cylinder, priced at $80,000, seemed to be the only solution to curb inspection expenses. The company began to explore other options. At Lambda, our primary approach to component enhancement and crack mitigation is through the introduction of designed or engineered residual compression. This proved to be a much more cost-effective solution to the MD-88 landing gear concerns. Engineered compression can negate tensile stresses from normal operation without altering the original material or design. Compression can be introduced to the critical areas through mechanical surface treatments like shot peening, laser shock peening, deep rolling, or low plasticity burnishing. The depth, magnitude, and distribution of the residual compression are designed specifically for each component and application to optimize the part's performance. This process begins with calculating the minimum residual stress required to mitigate fatigue and stress corrosion cracking. We do this using our proprietary fatigue design diagram. Knowing the mean and alternating service stresses, we can determine the amount of compression needed to provide damage tolerance sufficient to avoid failure for the component design life. This is indicated by the triangular region marked safe in the diagram. When the fracture-prone region is in a fully compressed state, the tensile stresses are absent, and therefore cracks cannot initiate or propagate. In the MD-88 landing gear example, compression of -180 kSI was applied to a depth of 40,000ths of an inch to restore nominal fatigue strength to the damaged surface. A request for an alternative means of compliance, or AMOC, was submitted to the FAA with detailed plans for testing and implementation. Once the engineered residual stress field is designed, the next step is processing the component. At Lambda, we use low plasticity burnishing as our primary tool for introducing engineered compressive stress. LPB has been shown to completely eliminate SCC in high-strength steels, making it an obvious choice for this landing gear application. LPB produces highly controlled, repeatable compressive stresses and leaves a smooth, mirror-like surface finish on all processed parts. More benefits of LPB can be found on our website. For initial testing, LPB was compared to shot-peened and as-machined conditions using 4-point bending fatigue specimens and C-ring specimens machined from the 300M landing gear itself. LPB treatment produced a significantly greater magnitude of compression at 10 times the depth of the shot-peened specimens. The high cycle fatigue and corrosion fatigue performance of LPB-treated 300M steel was compared against shot-peened and baseline conditions. Corrosion specimens were prepared by wrapping tissue soaked in 3.5% salt solution around the gauge section. Damage was simulated with a semi-elliptical 0.5 mm EDM notch. High cycle fatigue testing was conducted in 4-point bending on all specimens. Results showed that while undamaged specimens performed similarly under all processing conditions, damaged LPB-treated specimens significantly outperformed both as-machined and shot-peened specimens. Stress corrosion cracking tests were conducted on C-ring specimens made from 300M steel landing gear. A bolt was used to apply uniform tension to the outer surface of the straight gauge section. LPB-treated and as-machined specimens were subjected to alternate immersion stress corrosion cracking testing in a neutral 3.5% sodium chloride solution. Untreated material failed in only 261.8 hours at 150 kSI, 166.5 hours at 165 kSI, and only 12.9 hours at 180 kSI. The LPB process specimens did not fail even after 1,500 hours of exposure at all 3 stress levels. When the specimens were loaded to higher stress levels in an attempt to force failure, the specimens were severely bent without ever cracking. Additional testing was performed on specimens treated with shot peening and LPB at 165 ksi with and without a 0.5 mm EDM notch. All of the smooth shot peen specimens failed between 668 and 1,127 hours. Shot peen specimens with an EDM notch all failed within 3 hours. Once again, all LPB treated specimens ran out at 1,500 hours with or without the EDM notch. This indicates that the compression applied with LPB fully mitigated the effects of stress corrosion cracking. The FAA approved the AMOC. All MD-88 landing gear in service have now been treated with LPB. The LPB process was carried out at the airline's MRO facility using robotic equipment. In-situ application during regularly scheduled maintenance allowed for seamless integration into existing routines without service disruptions, improving fleet readiness while reducing costs. The LPB process has proven to be a highly cost-effective method of improving fatigue strength. Over $10 million in inspection cost savings alone was estimated when the AMOC was introduced. This savings estimate would be much greater if inflation, grounded plane costs, scheduling disruptions, and cylinder replacements were factored into the analysis. For more information or to discuss your application, please visit our website at lambdatex.com or call us at 513-561-0883.